You want to calculate some joint probability. Usually you'd have to peel off the variables one by one. You peel off a variable. So this is the definition of conditional probability. It's the joint is this guy conditioned on these guys times the probability that these guys are in that configuration, right? So like the probability that I'm cold and tired and hungry and have a late assignment is the probability I have a late assignment given that I'm cold, tired, wet, and hungry times the probability that I'm cold, tired, wet, and hungry. Does everyone understand this? Does that make intuitive sense? Okay, so we saw this formula yesterday, and the idea is that you have all of these, to compute the full joint probability of a particular world, you have all of these conditional probabilities where each variable is conditioned on all the ones that go before. And if we have a Bayes net, instead of being dependent on a whole bunch of variables, we're just dependent on the parents. So we have these little conditional probabilities to add up, or to multiply together. So it's a lot easier. The Bayes nets are a lot easier to deal with. Now the canonical query for a Bayes net is, what's the distribution of some variable of interest given that I know the values for some variables and I haven't observed some other variables? These are like the nuisance variables. All right, that's the sort of canonical query. So today we talked a little bit at the end of last class about approximate inference, and we're going to do that, and we're going to do exact inference today. So I talked about how to sample according to the joint last time. You just treat the Bayes net as a generative model, and you start with the top variables and sample. And so you set earthquake to true with probability this, and burglary true, and then you're sampling according to whatever probability distribution is specified by the CPT according to the parents. These folks have no parents, so they just have this unconditioned distribution. So that's how to generate worlds. And linear time in the size of the Bayes net, which is beautiful, as long as you already have it in topological order. But how fast is topological sort, all you algorithms folks? Linear time. So it's linear time to sample according to Bayes. And that's how big a sample is, right? A sample contains a value for every state. So you can't get any faster than that. So it's super fast to generate worlds. Now, what if we want to answer one of these queries where we don't just want to be able to sample the full state of the world, we want to know about some particular variable given that we know values for other ones. What do we do there? The very simplest thing you could possibly think of, given that we now know how to sample from the distribution. So, given that John and Mary both called, what's the probability there's a burglary? How could we figure that out?
Generate a bunch of worlds and then look at the ones that have E.
Yes. And then count up the whether the X is true or false. Exactly. So that's called rejection sampling. So you just sample and you reject the ones that don't match your evidence and look at the others. And the more if you take a single sample, you have some evidence about the probability of burglary. Like with a single sample, you have some evidence. The more samples you get, the better your estimates are. So it's an anytime algorithm. And in order to get the exact right answer, you have to run forever. So that's too bad. It's approximate. But it's awesome anytime performance. The more samples you get, the better things go. Now, right, it's like if it hails softballs, and I did once. Do you guys remember over in Exeter? When I was growing up, I lived in Massachusetts, and I remember hearing news reports about an auto dealership in Exeter that lost their entire inventory because there was like softball-sized hail that shattered the windshields of cars that were parked outside. So, yeah, like, does hail even come that size? Like, I have seen hail that's like that size, but like, I'm not sure I've ever even really seen golf ball-sized hail, but I know it happens. But you've seen softballs?
Not here.
But,
I was in Ohio.
How big was it?
It was like, I don't know, like that big.
Does it like make sounds? It must.
Oh yeah, one hit me in the head.
That's the explanation.
I mean, it hurt quite a large amount.
I mean, everyone must just like scream and run for cover?
Oh yeah.
Wow.
I mean, we didn't like notice that it was hailing. We were like on a walk or something. And it was like we didn't know it was like gonna start hailing on us.
You didn't know it was going to start hailing golf balls?
Yeah.
You should have predicted it.
So that's exactly. So if you want to know what's the probability, if we're interested in something about like, okay, how much does it hurt to get hit by like if it's hailing golf balls, what's the probability that I'm going to end up in the hospital with a concussion? Then we have to sample worlds until we get one that does match the evidence. So you have to keep sampling worlds until we get to the golf ball hail world, and then we look and see whether you're in the hospital with a concussion. Right? So this is going to be extremely inefficient because it's very unlikely that we'll have golf balls. It does happen, but you'll have to take like 1 million samples. Like how many days have you been alive for? Probably, like I don't know, 300 times 20 was a rough guess. So that's 6,000 days. So 6,000 days, only one of them had golf ball size hail. So has anyone else experienced golf ball size hail? So then we know that over 10 people. So that means you have to live 60,000 days on average before you get a golf ball-sized hail. So we're gonna keep 1 out of 60,000 samples. So this is extremely easy to implement and extremely slow if the evidence is unlikely, because very few worlds will match, and you'll be like Mr. Rejection. They all get rejected except for 1 out of 60,000. Yeah. So that's too bad. So what do we do about that? Darn, I wish those variables would come out to match E. But I'm the programmer. What can I do about it? Set them to E. Yeah, duh. But now you're like, oh, crap, I'm not sampling from the distribution anymore. So now I have to be clever and know a teeny bit of math. So So we're going to do this little sneaky thing. Okay, we go down, and it's just like sampling, except if the variable we're looking at is one of the ones that we have evidence about. Oh, by the way, just happens we're going to set that variable to be whatever the evidence says. But then we keep track of, okay, how likely was that? That thing we just did. Right? We just set VI to VI because that's what the evidence said to do. What's the probability that given whatever values I already have for the parents of VI, what's the probability VI would come out that way? This should probably be a capital VI here in the parents because we're talking about the variable here, and that's the value that we're using. What's the probability of that value given the values we have for the parents? All right, we keep track of that probability so that if it's very unlikely that, like, given that it's sunny and that we're walking in Ohio, that the size of the hail is golf ball, if that's like a 1 in 60,000 thing, we write that down and we say, oh, we have this weight that's 1, but every time we do something kind of radical and we force the world into this unlikely state, we write down how improbable that was. Okay? But it does have that value now. And every time we're at a normal variable, we just do the same thing we always do. Just look at the parents, sample, life is good. Now, when we're done, we're going to have a complete world, and it's going to have a weight associated to it according to how unlikely it was. But every single sample we take is going to have the right evidence. So we're only generating worlds that are interesting to us. But what we've captured, we're weighting each world. With the ones where, given the values for the parents, v is unlikely, we're going to pay less attention to. Right? So we're like de-skewing the distribution. We're forcing some of the variables to have certain values, but then we're going to correct by recording how unlikely that was, and then saying, okay, this sample here that I took, treat that as a 1 in 1,000 event. All others, a normal sample would have 1,000 times more weight than this. Now we're weighting them all the time because we're always going to set the variable to match E, but the parents might have different values. So when the evidence is actually likely according to the parents, then that sample is going to count more. And then at the end, once you've taken 1,000 samples or however many samples you wanted to, normalize all the weights so that the total weights sum to 1. And then you just take, you weight, you do the same counting we would do before about x, but you just weight the counts according to the weights of the samples. All right, so that if this evidence is very unlikely, given certain configurations of the parents, those samples have less weight. But every single sample is meaningful now. So does that make sense? We're skewing the distribution, but then we're keeping track of how we skewed it and undoing it. So extremely intuitive. These approximate inference techniques are awesome because they're trivial to implement, they're easy to understand, they work, and they're fast, and they have good anytime performance. Like, just taking a single sample is a very fast thing to do, linear time. And the more samples, the more time you're willing to spend, the better answer you get. So if anyone ever handed me a Bayesnet, which no one has yet in my life, but you never know, I would totally do this if I needed to answer some query. Now, in order to have a good estimate, I mean, the question is, how quickly does this estimate converge to the true probability distribution for the variable we're interested in? We can use every sample, but we may have a very biased selection. If the parents are usually coming out in one particular way, then every sample is going to get the same low weight, and we're not going to see, we may not have very much control over whether we see the other configurations of the parents. So it might not converge as fast per sample. So that's a limitation of this technique. There are probably results about that, but I don't know them, so I'm not going to talk about them. Any questions about approximate inference in Bayesnets? We did plane sampling, we did rejection sampling, we did likelihood weighting.